Okay, I'd like to take some time to discuss the mechanism of the hydroboration-oxidation reaction. And I'm going to use this unsymmetrical alkene, and we know from reading our textbook and perhaps watching a previous video that the addition is anti-Markovnikov and it is syn addition. And so we can draw our product with an OH on the less substituted side of the molecule, and we can draw the newly added H on the same face of the molecule. And so I have a wedge and a wedge for the OH and the H. And of course, I added my OH, the larger part of water, to the less substituted side of the alkene. So that is anti-Markovnikov. We also make the enantiomer of this. You might see it drawn like that, where we don't include the hydrogen right here. We know that it's on a dash because the methyl's on a wedge. Sometimes we'll draw it, sometimes we won't. So here we have a pair of enantiomers showing the anti-Markovnikov and the syn addition, and we're going to then explore the mechanism as a means of explaining that anti-Markovnikov and syn addition. So I'm going to redraw my alkene down here. And I'm going to look at the two carbons on the alkene. Let me label them red and green. Those two carbons are different, of course, and we have two different halves of the alkene. The green half is a little smaller, less bulky than the red half, and so that's how we decide on the anti-Markovnikov addition. And then I'm going to draw the BH3 in a suggestive fashion. If I can get my blue pen back here. So I'm going to treat the BH3 like it has two halves as well. One of those halves is very big. Let's circle that in purple, the BH2 half, and then I will circle in blue the hydrogen half. Now, of course, these aren't equal halves, but we can think about it like this because it's the BH bond that's reacting with the alkene. If you remember, the boron has an empty orbital, so it acts as a great Lewis acid, and it's going to receive the electrons from this pi bond. And so it's going to line up to receive those electrons such that the large group on the alkene, and I'll circle the red carbon half, is opposite the large group on the BH3. And this is the lowest energy transition state, and so that's why we get the anti-Markovnikov addition, because eventually this boron here is going to be turned into the OH group. All right, so let's draw some arrows. I'm going to try to draw those arrows in red. So the pi bond attacks the boron, and then the BH bond attacks the pi bond and essentially becomes attached to the red carbon. So let's see what that does here. This is a new stereocenter, so I'm going to indicate some stereochemistry. And I'm going to fix this methyl because I want to indicate stereochemistry there as well. So you see how my hydrogen is now attached to the red carbon, and my boron is attached to the green carbon. And again, the larger portion of the BH2 is added to the less substituted side of the alkene, the smaller side. That is the anti-Markovnikov addition. And because these two red arrows happen at the same time, it is impossible for the hydrogen and the boron to be added to the opposite face of the alkene. They have to be added at the same time, and so they come down either on top of my screen or from behind the screen to make the enantiomer. In this case, I've indicated they came from in front of the screen. And so that's where we get the syn addition as well. So let me just make a note of that. So all the interesting things happened already in this first step. The rest of the mechanism, which is a bit longer than, say, our average mechanism in organic chemistry, first semester organic chemistry at least, is all about changing this BH2 into an OH. And you'll notice there are two more BH bonds. So actually, this can happen twice more using the same boron, and we end up with a molecule that looks like this. Now I'm going to use R to indicate the other two alkenes that have been added. But two more alkenes can react with the same boron, and we get essentially a Br3 molecule. And we can abbreviate that Br3. That may be easier for us if we use Br3 for the rest of our mechanism. All right, so now this is step 2. The first step is to activate our peroxide, and that happens by taking the base, deprotonating the peroxide to make a hydroperoxy-anion. And that's what does the chemistry for the rest of this mechanism. And so this boron again has an empty orbital here. It can be attacked by the hydroperoxy-anion, and that gets us to this molecule here. And I'm going to draw all the R's now, because the R's actually move off the boron, so that plays a role. We have a minus charge on the boron. Don't forget about that. And so now we can take advantage of the instability of this OO single bond. We actually have a decent leaving group under basic conditions in the form of the OH minus right here. So let's take an R group, take its electrons, and I'm going to use red here, I think, just to see it a little easier. Take its electrons and move it onto the O and kick off OH minus. So we call this a rearrangement. It's not a carbocation rearrangement, but it is a rearrangement of the bonds in the molecule. And so what do we get here? Well, when I'm faced with a rearrangement, I like to try to draw everything in the same place without the bonds. So that means I would have a B and an R, another R there. I still have this BO bond. I don't have the BR bond on top, but I have an OR bond right here. And then I have an OH minus right there. So you can see that I've made a new R to oxygen bond. And indeed, that's what we're doing. Here is where the R is bonded to boron. Eventually, it's going to become an OH group there. And so we've basically made that bond now. Now our task is to free up this OR group, protonate it, and we'll be done with our reaction. This happens twice more. We can make a bunch of BOR groups. So every boron to R bond can be turned into a boron, or I'm sorry, an R to oxygen bond. And then we've got plenty of base around because we started with base and we're creating base every time we break one of these OO bonds. And so we can essentially add a base to the boron. That gets us to a 4 bonded boron, where we are ready to lose an OR group, like this. Any one of those could fall off, and in fact we do this same step 3 times. But here's the key feature. We form this OR minus molecule, and I'm going to erase the R now, and I'm going to actually draw it like it should be so we remember what the R looks like. So there's the OR molecule, the OR minus, and that can be protonated simply by having some water present, and we're in base and peroxide, so there's plenty of water around. And let me try to do this in red as well. And that gets us to our final product, which is ROH, but I'll draw the whole thing here. So I hope you can see that the hydroboration mechanism is not that scary. It is complex, it is long, but it's something that you can do. So you can watch this video again, you can find another video. Definitely look at the page in your textbook that has it as well.